All right, good morning, everyone. My name is Tom Lendacky. I work at AMD on the Linux kernel team, focusing mainly on confidential computing technologies. And today I'm going to talk to you about VM privilege level feature of SNP and how we are going to use that to create levels and execute within those levels and why we would want to do that. All right, as a first thing I'm going to do a review. I'm going to go through the SEV review pretty quickly. Hopefully most of the folks know a lot about that already. And then I'll focus a little bit more on VMPLs and the Secure VM Service Module, or SVSM. And then we'll get into exploring some options on how we can create these VMPL levels and how we can switch between them. SEV, and Paulo talked about this a little bit this morning already. So it's a way of having a guest protect itself from the hypervisor and from other VMs on the system through cryptographic means. So every guest gets a unique ASID, or address space identifier, which gives them then a unique encryption key, and we encrypt the memory in that key. SEV-ES is the next step in that, and that's where we encrypt the guest register state so that the hypervisor can't see the register state as the guest is executing. We split out the save area, which used to be part of the VMCB itself. In order to do this, that save area is encrypted. Every time we do a VM run, we decrypt it, load that guest state into the guest, and on VM exit we save that back into the save area. That does present problems if you're trying to have the hypervisor do certain things for you. Paulo mentioned like an MSR read. CPU ID is another thing. We use an unencrypted page or a shared page in a standard where we can communicate state to the hypervisor and get the answers back, and that's how we can handle that without divulging too much state to the hypervisor. Secure nested paging is the next step, and this is where we add integrity protection to our confidential computing model, and we do that through the reverse map table, or the RMP. This gives us a one-to-one mapping between a guest's physical address of a page and the system physical address in the system in general. We maintain metadata information in that RMP table about who owns the page, what size the page is, whether that page is a VM save area page, things like that. So this is the main area that I want to talk about, which is VM privilege levels. It allows you to divide up your guest address space in up to four levels. VMPL 0 is the most privileged level, and so if you have a service running in VMPL 0, you can protect that service from lower VMPLs, lower privileged VMPLs. The VMPL level is contained in the save area, so when a VM run is done, that's how the hardware determines what VM privilege level it's running at. And within each RMP entry that represents a page in system physical memory, we have permissions associated with that, and those permissions are what decide whether or not a particular VMPL level has access to that page, or the type of access it has to that page. So how do we use VMPLs? This is where a Secure VM Service Module comes in. In particular, we've been working closely with the Coconut SVSM project. There are certain services that you can run within that SVSM. to provide that service to the guest without it being in the hypervisor. You know, a typical example is a VTPM. Normally in a hypervisor environment, it's the hypervisor providing the VTPM, and you can't trust that in a confidential computing environment. So you can run this service at that higher VMPL level and allow the guest to make use of that. Another use we are planning on doing is live migration through there to ensure that all the pages that are modified by the guests do get migrated to the destination. And Pankaj will have a talk tomorrow on live migration. So if you're interested in that, that would be a good thing to attend. How we transition between VMPL levels, fairly simple. We have AP requests, AP create requests, or hypercall requests that we use the GHCB for. Once you create that, it will typically just start running at that VMPL level. And when you want to change, this is where the SVSM specification comes in. You set up your register state. You set up the request in a calling area page, and then you ask the hypervisor to now switch to the different VMPL level. At that point, KVM hypervisor loads, saves any information it needs from the previous VMPL level, loads the new VMPL level, issues a VM run, and you're now running in the requested VMPL level. When VMPL 0, in this case, say, wants to transition back to the guest, it's just going to say, okay, now run VMPL 2 in this example. So it's always up to the running guest code to request this switch. KVM will just always perform a VM run with the VMPL level that it needs or is last asked about. I'm going to talk about 3 possible approaches. There are more, and after LPC, there's yet the one that probably is going to be used that isn't listed here. But it's a kind of hybrid of something here. You can have a VM where you have each vCPU in the VM contains all the different VMPL level context. Or we could have a VM where each vCPU is a dedicated VMPL context. Or you could have, and when I say VM, this is a KVM struct, VM struct that's returned back on a create VM call. So you could also have a VM, a guest VM that has 1 VM per VMPL level. The picture that I'll show later will make that a little clearer. So let's get into talking about these different approaches and how we create and transition between them. So in the first approach, you could have 1 VM and each vCPU has all of the VMPL context. Everything stays within KVM at that point. When we go to create the vCPU VMPL level, it's just a request from the guest. We save the information from the guest, kick the target vCPU, and let it validate the input and start running at that point. Execution-wise, if you're running and you want to switch to a different vCPU VMPL level, then it's merely switching fields from the context, particularly the VMSA pointer, which points to, in the VMCB control block, which points to the save area that will have the VMPL level that you're interested in. There's a few other things like the GHCB, some tracking registers that KVM uses that we also would swap. And as soon as the hypervisor does a VM run, you're running in that requested VMPL level. So some of the pros, it's fast, right? We never leave KVM. We switch over to the hypervisor, make some changes, and then issue a VM run. VMM agnostic. VMM doesn't have to know about VMPLs. We'll find later that we are going to need the VMM to know some things if we start putting devices into an SVSM, and we have to possibly do interrupts or IPIs or something into the VMPL 0 level of the like Coconut SVSM. But for now, you know, we don't envision for this approach to require any changes. But we have to save and restore particular fields. And some of the fields are in the VMCB control block that when a guest exits get modified. Some are just pointers to things like the save area or the current GHCB. But that could be a little delicate as far as, you know, newer hardware could introduce something that modifies the VMCB slightly to return some information, and then that's another piece of context we have to save. So it might be a little brittle in that case, right? And then APIC support, as I mentioned with interrupts, we probably need separate APIC instances. We're going to have different interrupts possibly assigned to different VMPL levels. So that's going to require work on that side to be able to maybe create new APIC instances and associate those. One of the other options is to do a VM, and each vCPU is a dedicated VMPL level. So you would have this logical vCPU 0 that would have under it physical vCPU structures that represent the different VMPL levels. Now we're at this point outside of KVM alone, and so when a request to create a new VMPL level comes in, that's going to have to go up to the VMM. At that point, the VMM will need to start running that VMPL level, new VMPL level, and all the validation and translation will happen on that new run. Kind of same thing for changing VMPL levels. We're going to have to send that request back up to user space, and then user space would have to pause the current vCPU VMPL level and resume or start the target one. So the pros on that, we maintain easily all this context information because it's associated with the vCPU structure. We have separate vCPU structures, so we don't have to worry about have we saved enough information? Are we restoring enough information? We have separate VMCBs, separate VMSA, separate GHCB pointers, everything like that. The cons are that we have to transition to user space. When we start now having multiple vCPUs, it becomes a little more difficult for vCPU pinning. The VMM is going to have to know that if you want to pin vCPU 0 and you have multiple threads for each VMPL, you're going to have to track those and make sure that you pin those appropriately versus just a single thread. Interrupt routing. So there was the patch series from the VSM folks, VTL folks, that introduced namespacing, and you would have to make use of that in QEMU, so we would have to add namespace support into QEMU so that the vCPUs could be easily discerned between APIC ID and VMPL level now. KVM would also require some of that, so interrupt routing becomes a little trickier, and in I think the current version of the patches that I set up that I'll reference later, we basically just say we're not going to inject any interrupts into one particular VMPL level. So it makes it easy, but that would be something that would need to be taken into account. The last approach that I'm going to talk about is having one VM per se per VMPL level, right? And so now we separate out the vCPUs from the other vCPUs. You have to know about the relation of vCPU 0 in one VM to vCPU 0 in the other VM. The request is sent up to the VMM. It creates new CPUs within the new VM that's created. And that new vCPU validates and translates when it runs the information. Similar execution flow, though. Up to the VMM, it pauses one thread, starts the other thread, right? Similar pros, too, to the previous method in that all our context information is separate. You know, we don't have to worry about saving and restoring specific data. It's all present. Similar cons, we have to transition to user space. QEMU isn't really set up to understand all this, so it's going to be significant VMM work to do something like this. We'd have to maintain VM to device association so that we can route things properly. And currently with GMEM, we can't share GMEM between multiple KVM structs, KVM VMs. There is work being done by Ackerley at Google to try and change that, but right now it doesn't exist. So for a summary, which approach is best, right? I put out an RFC recently to do the first approach, and Roy Hopkins is somewhere, there he is. He put out an RFC that did a hybrid approach of having separate vCPUs within a single common area within the vCPU, and it's sort of like the second approach. We're currently in the proof of concept only supporting 2 VMPL levels, but we should probably be set up to support more if somebody wants to run more than that. The big thing, though, is we have to avoid transitions to user space in order for the VMPL switch to be fast. So we need VMPL switches to do validation of memory acceptance. Melody, who is on our team, is going to talk tomorrow about alternate injection, a feature in SNP for secure interrupt delivery. You can imagine if you're dealing with interrupts that VMPL switches could happen quite a bit, so we need to do that very quickly. VTPM, depending on how many measurements are being taken. So I'd like to say that rules out approaches to having to exit to the VMM unless we can figure out KVM optimizations, which, talking at plumbers, we probably have already. So we'll probably talk more on the mailing list about some of this. But it's almost like, I think the concept is almost like a nesting VM, calling create VM within the VM so that we can still maintain context between all the different vCPUs and VMPL levels. So more on that, I guess, out on the mailing list or in a BOF, yeah. So just some references for anybody that wants to take a look at some of this. And that's pretty much it. Any questions?
Just a question. So is VMPL 0 special in some way? Does hardware switch to it automatically sometimes?
It is special in that there are some like instructions that can only be done at VMPL 0. So a p-validate instruction can only be done in VMPL 0. So one of the protocols in the SVSM is for validating memory. So we have to go, if we're running at VMPL 2, we're going to have to go to VMPL 0 to validate memory.
So that's the reason you use VMPL 0 for, and why, any special reason you're using 2 for firmware?
That was just an example.
Okay.
You could use 1, I think initially 1. I think Jorg maybe has a reason why Coconut's using 2. But you could use 3. It all depends on whether or not you're going to have other services that are running at the other levels that you want to be able to protect against.
So there's a lot conceptually here similar to VTLs, and I think it would be unfortunate if we end up with 2 different solutions. Yeah, so
we will not end up with 2 solutions.
Yeah, so with that in mind, I mean, if you look at where VTLs are going towards the per VM, Nicholas, is that still the plan? Yeah, you know, that's really what we need to do for VMPLs, and got to understand how to make those transitions fast or less important.
Right. I looked at the, I don't know if there's been any newer patches, but I looked at the GitHub tree where basically everything was going up to user space to make that transition. And so, yeah, we need to work on a way to not do that and still have.
We need to have basically something that allows for going to user space for a first implementation, but also allows not going to user space if KVM does the work to avoid that. Also because Will correct me if I'm wrong, but I think CCA will not necessarily exit to KVM across exits to different levels, and therefore in that case you just don't have the control. So you need an API that supports all the cases.
Yeah, but I don't think you can have an API that supports exiting from a different vCPU that you entered from, but still compatible with this. I think if TDX and CCA want to do games where the never say never, but no, I think if the trusted module causes an exit on a different vCPU than KVM entered, then it has to be the same vCPU from KVM's perspective, and you just lose the ability to introspect one and not the other.
So same vCPU ID, but not necessarily same vCPU privilege level.
Right, but I'm saying in that case, they need to be the same vCPU logically from KVM's perspective. You don't get separate interrupts. And if you want separate interrupts, give us an API that KVM can actually intercept the transitions.
Yeah, I mean, we need to design that. That needs time. We can discuss it. We will see. I'm not too pessimistic, but of course you may be right.
And I think the other thing with the fast switching would be useful irrespective of confidential computing. I can imagine an oversubscribed scenario where you're running vCPUs on the same CPU, and we already do this to some extent in KVM with the positive exiting detection that the vCPU is spinning and yielding to a different vCPU in the same VM to try and release a spin lock. We could do something similar where if user space knows that it wants to run a different vCPU, give it a way to quickly switch without having to exit, in theory.
So it sounds like the way to go here is to switch to your RFC patches to switch to the per VM per VMPL and be slow and go up to user space for now, and then work on optimizations over time to improve the switching.
So first of all, there are, as I'm aware, 4 technologies that we want to support with this level switching approach. That is VSM that AWS is working on. There's VMPLs from AMD. There's TDX partitioning and ARM-CCA. And the last 2 actually support level switches from within the VM, so you can have a privileged level switch without having a VM exit. That's something we need to support, and I think we agree on that. But something we also need is actually separate interrupt sources per level, because the users that we are doing this for, which are non-enlightened operating systems, actually rely on having different interrupt sources or separate interrupt sources per level, and this is something very important to support as well. So
I think this is where we push back on Intel and ARM to fix their implementations. Like it's to some extent. I mean, TDX partitioning, it's not upstream. We don't even have TDX upstream. Like, if the only concern is that you can see into the guest transitions, that's a ridiculous reason not to exit.
I agree that that's not the reason, but I think if we can make the TDX case close enough to the accelerated case, we might not need that. Like, I'm okay with asking TDX to fix some stuff, but you know how that has gone so far. So I'm more optimistic on being able to do something with a good design in KVM than actually having what we want in TDX or CCA.
It's also not just about the design, but inabilities to do that, right? It's also part of performance penalties. You just pay for these additional round trips. The same way they're trying to avoid user space round trips. The next level up is really just to avoid a low visor exit. We had a small buff last week at LPC where Paolo has interesting ideas on how to actually make that happen, and I think I like them so far. I think they will work. So let's talk about this in the buff. We don't have the 2 minutes left on this talk to go in and actually go. Is it 4? Oh, 4 minutes. Sure. I don't think 4 is enough.
Let's change the topic of the questions.
And dive into this really deeply, right?
With regards to VMPLs, do you foresee having asynchronous entries into higher privileged VMPLs? No? Like, can't you set up a timer and for the timer to kick in at some point? Yeah. Okay. Okay. So that needs to be supported from day one. Yeah, in API.
Right. All right. Thank you all.